Good morning, students. So we are learning about the computer instructions, right? And we discussed about data transfer instructions and data manipulation instructions. The third type of instructions, okay, are program control instructions. So we are going to discuss about these program control instructions in this class. Program control instructions. Okay, these instructions are used to control the flow of execution of the instructions in a program. That means these instructions are used to control the order of execution. Okay, order of executions of the instructions in the program. Generally in memory, okay, when the set of instructions as a program, when the instructions are stored in memory, they are stored in consecutive memory locations. Okay, the instructions of a program are stored in consecutive memory locations, and the instructions are executed one after the other in sequential order. Okay, this is the sequential order of executing a program. The first instruction that is stored at the first location in memory. Okay, how this location is identified? The program counter. Okay, we have a register called program counter. Okay, the address in this particular register that denotes the address of the instruction that is to be executed. So first, when the set of instructions are loaded in memory, when the set of instructions are to be executed, this PC will be holding the address of the first instruction, okay, initially. So the instruction pointed by the PC is executed first, okay, that is, it is fetched, means it is moved to instruction register and then decoded and executed. And once this instruction, okay, this is first instruction, and then the second instruction, third, fourth, and fifth in a serial order, okay, in a sequential order, the instructions are stored. So the the program counter will be pointing to the first instruction. When this instruction is fetched for execution, PC is incremented by 1. Okay, so PC will be pointing to the next instruction. Okay, so this says that the next instruction to be executed is instruction 2. Okay, that is at the next consecutive location. So this way, using the program counter, generally the instructions are executed in a sequential order by incrementing the program counter by 1. There may be cases we need to alter the sequence. All the times we may not need to execute the instructions in this sequential order. Okay, we may like to change the order of execution. There may be subroutines that are stored in some other locations. Or we may like to change the order of the execution based on some conditions. Okay, if this condition is true, this particular part of this instruction, okay, need to be executed. Or if the condition is false, we don't want to execute that instruction. So the control has to move to the other part of the program, right? To a different location to execute that instruction. So these all can be done by this program control instruction, okay, changing the order of execution. So the program control type of instruction, when executed, may change the address value in the program counter and cause the flow of control to be altered. So how the order of this execution, okay, sequential execution can be altered by changing the value of this program counter. Correct? This is the register that tells what is the next instruction to be executed. So how it is done? When this type of instructions, program control type of instruction, when it is executed, it loads the address that is there in the instruction to the program counter. Otherwise, program control will be pointing to the next instruction. To change that, okay, the address given in the program control instruction, what is being executed, is loaded into the program counter. So that will be considered as the next instruction. Okay, the instruction at that location that is loaded into PC will be the next instruction. This way, we can change the order of execution of statements. So the second point here, the change of value in the program counter as a result of the execution of a program control instruction causes a break in the sequence of instruction execution. Based on the address that is stored in the program counter, the control may be taken to a different instruction that causes a break in the sequence of instruction execution. And this is an important feature in digital computers as it provides control over the flow of program execution and a capability for branching to different program segments. Okay, using this feature, this is an important feature which can be used to change the order of execution by branching to some other locations to execute those instructions. So here we have a set of program control instructions, okay, given in this table. Branch instruction, the mnemonic used is BR. Jump instruction, it is also used to control the program flow of execution. JMP, the mnemonic used is JMP. Skip instruction, call, return, compare, and test. Okay, these are all the program control, commonly used program control instructions. So let's see this one by one. Branch. Okay, the first instruction is branch with a mnemonic BR. This branch and jump instruction. Okay, we can take these two together. These two means the same. Both of these instructions are used to take the control to some other location in the program. Sometimes these two instructions are differently used to denote different addressing modes. The format is we write BR and then address. No, this is a location. The location of the instructions that is to be executed next. Okay, where the control has to be taken, okay, to execute the instruction. And to change the sequential order, this address is used. This branch and jump are one address instruction. Okay, always we give the instruction as BR and then ADR. ADR is the address to where the control has to be taken to execute the instruction. Okay, to change the sequential order of execution, if the control has to be taken to a particular address, okay, we write the instruction BR with the address. So how it is implemented? This address is loaded into PC. Okay, when this particular instruction is executed, the address in the address field, what is the address in the address field? Here we have denoted it as ADR. This is loaded into the program counter. Okay, so when the control has to fetch the next instruction, it looks for the address that is there in the program counter. What we have in the program counter is this address, okay, that is in the branch instruction. So the control will fetch the instruction that is at this particular location in memory. Okay, this way using this instruction, okay, BR or even jump instruction with a mnemonic JMP. BR and JMP are single address instruction. Okay, we give one address that is the location where to branch or where the control has to jump to execute the next instruction. So now moving the control to that location is done by changing the content of the program counter. Okay, loading this address into the program counter, the address given in the instruction. Okay, JMB ADR. Okay, this is moved to the program counter. Okay, and these instructions may be conditional or unconditional. Okay, depending upon conditions, if we want to do this branching. In such cases, we give conditional instructions here. And when this is unconditional, it can be used as a conditional instruction or unconditional instruction. When these instructions, JMP and BR, branch and jump, are used as conditional instructions, we give some conditions. Okay, there's some condition has to be checked, and based on the condition, the control moves. Okay, whether to follow the sequential order, or if the control has to move to this particular address, that is decided by the condition given. Okay, based on the condition. If the condition is met, the control moves to this address given in the instruction. If the condition is not met, the control will not move to this address. It will follow the other sequential order. Okay, this way, based on the conditions, we can implement this. Okay, branching, whether to branch or not, can be decided by checking some conditions. So these instructions can be conditional or unconditional. If suppose location, 1000. Okay, here we have our first instruction. Initially, PC points to this particular location, right? The value of PC would be 1000. So this is the instruction that is to be fetched and executed. And after this, once this is fetched, PC will be incremented to point to this particular location. Okay, and we have some other instruction. Okay, let's say some set of instruction we have at location 2500. Okay, and here we have a branch instruction. Our second instruction is BR and some address. Okay, address is 2500. Okay, so how this is executed? After fetching the first instruction, PC will be pointing to this. So this is the second instruction to be executed. So this instruction is fetched, and during execution, once this instruction is fetched, PC will be pointing to once the second instruction is fetched, PC will be pointing to the third instruction. Okay, because this is the instruction that is to be executed next. And during the execution of this instruction, it is found that this is BR, okay, means branch instruction. And so the meaning of this is branch to this particular location. Okay, so when when the operation code is decoded, the computer understands that it is to branch to other location. So what is the operation performed? When this instruction is executed, this address in the address field, that is 2500, is moved to the program counter. So our program counter, okay, will have 2500 instead of 1300 or whatever is the address of the third instruction. Okay, instead of this, the PC will have 2500. And after the execution of this instruction, as PC has this value 2500 in it, the control will jump to this particular instruction to execute this. Okay, this way branching is done. And the next control instruction here listed is skip. Okay, the third one is skip. The mnemonic used is SKP. This instruction is not to branch to some other location. This is used to control the flow of execution by skipping the next instruction. Okay, SKP is a zero address instruction. We don't give any address here as we give in BR and GMP. Okay, here we give the address where to branch. But SKP is an instruction. The skip instruction will not have any address in the address field. Okay, it is a zero address instruction. Always when skip is given means to skip the next instruction. The next instruction is skipped. Okay, example, if PC is 1000, okay, and it is pointing to the first instruction. Okay, this is means, so this particular instruction is executed. And if the next instruction is SKP, okay, instead of BR, we have SKP. This is our next instruction. So after fetching the first instruction, PC will be pointing to this. When SKP is executed, generally once this instruction, this is our second instruction. Once this is fetched, PC will be pointing to the third instruction. Okay, but our second instruction is SKP. So this will increment the PC program counter by 1. So it will now point to the fourth instruction. Okay, so this way the next instruction to be executed is skipped when we have the skip instruction. Okay, and here we need to note that this increment of PC, okay, for skipping the instruction, it is done in execution phase. Correct? Generally, PC is incremented during fetch phase. To recollect what all the phases of instruction cycle. The first phase is fetch, right? Fetching the instruction, okay? And in this phase, PC is incremented. Okay, fetch phase is to fetch the instruction, means moving the instruction from the memory to instruction register for execution. And second is decode. Decode is to decode the instruction or split. The instruction will have different parts. the opcode and the mode field, and we have address field. So splitting those fields and moving it into different registers and finding the decoding those, the operation to be performed. Correct? That is decode phase. And the third phase is finding the effective address. In case of indirect addressing, we need to find the effective address because it is indirect. In case of indirect addressing, we will not have the effective address in the address field. So finding the effective address, that is the third phase. And finally, once the effective address is found, fourth is execution phase. And during this fetch phase, generally PC is incremented. Okay. What all the micro operations that are performed during fetch phase? The PC will have the instruction that is to be fetched. So to fetch, that is moved to the address register, right? This is the first instruction that is done at T0. Okay, we have done this, writing here to recollect it again. And the memory word at this location. Okay, the address at PC directly cannot be used. So it has to be moved to the address register to get the instruction from that location. Okay, that is the first micro operation. And the second micro operation is memory word at address is moved to instruction register. Okay, so we get the instruction in this instruction register, and at the same time, once this is fetched, PC is incremented. Okay, so PC is PC plus 1. You remember these statements? This is done at time T0, and this one is the second micro operation. Okay, these two operations are done at time T1 in fetch phase. Correct? Okay, instruction is fetched at the given address from PC, the location pointed by PC. That is moved to instruction register. So that is fetching the instruction, and once it is fetched, PC is incremented. So here PC is incremented in fetch phase itself for sequential execution. And in this skip instruction, okay, when skip instruction is executed, PC is one more time incremented, but this is done during execution phase. Okay, during execution of this particular instruction. Okay, here in our example, the second instruction is skip. Okay, so PC, the value of PC, when this instruction is fetched during fetch phase, PC will be this. Let's say this is 1001. Okay, and this is 1002 and 1003. Okay, let's assume that this is the addressing. So the second instruction is skip. Initially PC is 1000, and when it is incremented after fetching the first instruction, so it is pointing to the second instruction. And once the second instruction is fetched, PC will be incremented. So PC will be pointing to this instruction. Okay, so it is 1002. And during the execution of this instruction, the instruction is a program control instruction. Okay, so this instruction is, the meaning of this is to skip the next instruction. Okay, how that can be done? Skipping of next instruction. The program counter value need to be set, correct? Changed, because PC is pointing to the next instruction. To skip the next instruction, PC is incremented. Okay, so PC will be pointing to the fourth instruction. This way, third instruction is skipped. So this is done using this increment of PC. Okay, program counter is done in execution phase. Okay, this is a skip instruction. It's a zero address instruction. It is always to skip the next instruction. And the next instruction, call and return. Okay, these two instructions are used with the subroutines. Call instruction is to call the subroutine. Okay, when a subroutine call statement comes, the control has to be taken to execute the subroutine, right? Taken to the location of the subroutine to execute that. And once that execution of those statements are, set of statements given in the subroutine are over, the control has to return back to the main program, correct? Okay, so for that we have return. Okay, it is given in the subroutine. Last statement of subroutine is to return to the main program. So these are used with subroutine. We will discuss about these two statements, call and return, separately. And before that, we have two more instructions, compare and test. The mnemonic used is CMP for compare and test. Okay, TST. The mnemonic used for test is TST. This compare operation, okay, this is used to compare two operands. If the two operands are A and B, this compare operation performs subtraction on the given operands and it will not store the value. Okay, we don't want the result of subtraction, but based on the result, some status conditions are set. Okay, this compare sets some status conditions. Like if suppose there is a status flag, okay, and if A is greater than B, the value need to be 1. If A is not greater than B, the value to be, okay, value in this flag should be set to 0. Okay, such condition. This is a status condition that need to be set based on the value of A and B. Okay, so in such cases, we use this compare instruction. Compare instruction is to compare the two operands. It compares by subtracting, and after subtracting, it based on the result, it set the status condition. Okay, and this test instruction. Okay, A and B are the two operands, but this performs AND operation for testing the value, okay, or the relationship between the operands A and B. If both the bits are 0, okay, to check if both the bits are 0, or if it is both the bits are 1, okay, if it is 1 and 0, okay, this way to check the operands. So such cases we use this test. Okay, test by performing AND operation. Performs AND operation on the given operands, and based on the result, it sets the status flag. Okay, if suppose the result of AND would be 1 when two inputs are 1, the input values are 1. So if it is 1, the status flag need to be set 1, otherwise it is 0. Okay, so by this we can find out, okay, or in case if it is, we want to find if both the signs are, okay, 1 positive, both the numbers are positive, okay, the leftmost bit is checked. It performs and based on the result of AND, it sets the status flag. So these two instructions, compare and test. It performs some operations on the input operands, and based on the result of the operation performed, these are used to set the status conditions. Okay, based on the conditions, the control flow of the execution can be controlled. So what are these status bits? There are some flag bits that are maintained with the arithmetic and logic unit. Let's consider this ALU, okay, that has two input operands. Okay, the input registers are A and B here, 8-bit register. Okay, so ALU is performing an operation on two input data, okay, two input operands, A and B. And some operation is performed by ALU and it generates the output of 8 bits. Okay, and that is indicated by F0 to F7, 0 to 7, the 8 bits. Okay, this is the output. F is the output given here as output. And based on this operation, the ALU performs, we have some status bits. Here we have a register that has 4 bits. But these 4 bits individually indicate some status conditions. Okay, the first bit of this register indicates this carry. Okay, if there is a carry after this operation, if there is a carry or not. And the second bit of the register, okay, second least significant bit of the register indicates if the sign is 1 or 0. 1 means it is negative, and if the sign is 0 means it's positive. That is indicated by this particular bit, sign of the number. Okay, here is if there is a carry. Okay, after the operation, this flag is used to indicate if there is a carry, and this flag is used to check if the number is positive or negative, the sign bit. And we have the third bit of the register indicates if the bits are all 0. Okay, so we have a 0 flag here, is it? And we have this V flag that is to check overflow condition. After the operation, if there is a overflow. So this way, a register, a status, we call this a status register because all the bits of this, individual bits of the registers, if we take, these bits indicate the status condition, okay, status of the operation that is performed. Okay, so this is a status register, and individually these bits are called status bits. The first bit is a carry bit. Okay, C is the carry bit, and S is the sign bit. Z is the 0 indication bit, and V is overflow indication bit. So how these flags are set? The ALU performs, the ALU take 2 inputs, okay, from the 8-bit registers A and B, and performs some operation, and it generates the output that is indicated as F0 to F7. Okay, and there may be carry. Okay, once this operation is performed, the carry is indicated here as C8. Okay, C8 is the final carry that comes out of this operation. And the previous carry is indicated here as C7. C7 is the previous carry. Okay, I'll give you an example also. So these two bits are C7 and C8. And so here to check this, to set this V, okay, status bit V, the two carries are what is the overflow condition? Yeah, let's start from here to, that gives you more clarity. What is carry? How is carry bit set? When there is a carry, right? Okay, means if C8 is 1, when there is a carry, if it is 1, if the carry bit is 1, we add 1, 1, 1, 1. Okay, let's say we are performing a 2-bit operations on 2 bits. So 1 plus 1 is 1, 0, and here it is 1, 1. We call this as it is a 8-bit, okay, we call this as C8 and C7. In this case, 2-bit. Okay, so this is C2. Okay, here the first carry is C0 and C1. The second carry, final carry is C2. So if there is a carry, if the carry bit is 1, that means there is carry. Okay, so the carry flag is set after the operation. C8 is the carry bit. So this is checked. If this is 1, the value of C is set to 1. Okay, otherwise it is 0, depending on the carry bit. If there is a carry, or if the carry bit C8 is 1, this flag is set to 1, otherwise it is 0. Okay. And the sign bit, second one, sign bit. Okay, for checking the sign of the resultant data. The result is F0 to F7. So here F7 indicates the sign, right? If F7 is 1, that means the result is negative. And if F7 is 0, that means the result is positive. So we need to check this F7 here. F7 is checked based on the value in F7, the sign bit is checked. Okay, so the bit in the result used to set the sign bit. Sign flag is F7. If it is 1, the sign flag, okay, S is 1. And if the value of F7 is 0, it is set to 0. And this is it, okay, is it flag is to check for 0 output. Once the operation is performed, and if all the bits of the result are 0. Okay, so to check 8 bits, all the 8 bits are 0. Okay, so here that is passed through a circuit that checks for 0. Okay, and if it is 0, this flag is set to 1. The value of this flag is set to 1. If it is not all zeros, it is set to 0. And next is this V flag. Okay, we used to check the overflow condition. What is the overflow? When the operation is performed and when the result occupies more number of bits, okay, than what the register can accommodate, correct? Then we call it that condition as overflow condition. Overflow occurs when some arithmetic or logical operation is performed on two operands and the result is larger than the number of bits in the register. When we take 2 bits, 0, 0, 0, 1, 1, 0, 1, 1. So these 2-bit combinations are used to represent how many numbers here? 4, right? 0 to 3 means this is 0, 1, 2, and 3. This way, 4-bit, 4 numbers are represented using these 2 numbers, that is denoted by, that is found by 2 power 2, that is 4. Okay, when the bits are 3, when 3 bits are used, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Okay, so here 4, 5, 6, and 7. So these 3 bits, the combination of 3 bits are used to represent 8 numbers, right? 0 to 7. So 2 power 3 is 8. This way, when we perform an arithmetic operation, okay, here 8 bits. So how many bits the resultant register, okay, can accommodate? How many means, yeah, when it is 2 power 8, 2 power 8 is 256, right? Okay, so total numbers that can be represented using these 8 bits when we perform operations on 8-bit inputs, okay, 2 operands of 8 bits, the result will be of 8 bits, correct? So these 8-bit number can represent one of these 256 numbers. And if it is a signed number, okay, this is for unsigned numbers we are talking, okay, 0 to all unsigned numbers, 0 to 7, 8. If these numbers are signed, okay, how many numbers from it? It ranges from minus, in this case, minus 7 to, sorry, it is totally 8 numbers, right? Okay, so it is from minus 4 to plus 3, correct? This is the range of numbers, 8 numbers, minus 4, minus 3, minus 2, minus 1, 0, 1, 2, 3. Okay, the 8 numbers that can be represented using this 3-bit combinations. Okay, these are the 8 numbers. Same way, when there are 8 bits, it is from minus the range of numbers that can be represented as minus 127 or 128, yeah, 2, 0, 2 plus 127. Okay, these are all the 256 numbers that can be represented when the numbers are signed, correct? The 256, this is a range. So when the result exceeds this range, or when this goes beyond, when the resultant number, okay, after performing this operations on 8-bit numbers, when the result, okay, we get is, that lies beyond this limit, okay, beyond minus 128 and plus 127, okay, we say that there is an overflow. Okay, then the bits also, number of bits will not be 8, it will be more than 8. Okay, the register what we have here to hold the 8 bits will not be sufficient to hold this extra digits. Okay, so we say that the result will not be correct, definitely that case. So this conditions we call overflow condition. Okay, so here how we check the overflow condition, we have learned it. Okay, we check the carry. Okay, the 2 carries. C8 is the carry we get out of the operation performed, and C7 is the previous carry. So we compare these two. Okay, for comparing we use exclusive OR here. XOR circuit is used. When both these carries are same, okay, when these both are equal, it generates 0, right? What is XOR? XOR generates 0 if both the bits are same. So when these two are either 0, 0 or 1, 1, both are same, it generates 0. Otherwise, it is 1. Okay, otherwise, the value of output of this XOR would be 1. So if these bits are same, we say that there is no carry. Okay, so if B is 0, means there is no overflow. When these two bits are C7 and C8 are same, we say that there is no overflow. Okay, the result of this would be 0. And V, this bit is set to 0, means there is no overflow. When these bits are different, one is 1 and one is 0, means there is an overflow. Okay, this is what indicates the overflow condition. The bits C7 and C8 are compared. When the bits are different, okay, there is overflow. The resultant bits are beyond this limit of numbers that can be represented using the specified bits in the register. Okay, so this, to compare these two, we pass these, we perform exclusive OR on these two bits. And depending on the result this XOR circuit generates, this V is set to 1 or 0. Okay, so this way these status bits are used to check the status conditions. Okay, after the ALU performed, this status register is maintained with the ALU. Okay, in the CPU, we have the register that maintains the status condition. After the ALU performs the operation, based on the result, the flag is set. Okay, so if we take an example, let's take a 8-bit number. It's 10110011. Okay, if these are the 2-bit numbers, A and B. Okay, and let's say that ALU performs subtraction here. Okay, so the operation to be performed is A minus B. How is A minus B performed? B need to be 2's complemented. Okay, so when we find the 2's complement, 1's complement is 0, 0, 1, 0, 0, 0, 1, 0. And when you add 1 to this, we get 0, 0, 1, 0, 0, 0, 1, 1. Okay, this is the 2's complement of B. Now this has to be added to A. Okay, so A is 1, 0, 1, 1, 0, 0, 1, 1. And B is this 0, 0, 1, 1, 1. Okay, when we add this, it is 1, 0, 1, 1. Here is 1, 0, 1, 1, 0, 1. And this is 1. Here it is 1. And there is no carry, right? Carry is 0. So the carry that we need to we use to check for overflow is, this is the first carry is C0, C1, C2, C3, okay, up to C7. This is C7. What is C7 here? This carry is C7. Okay, and this is C8, the last carry. Okay, what is C7 here? After the previous operation is 1 plus 0 plus 0. It is 1. So the carry is 0 here. Okay. So to check overflow, these two carries are checked, C7 and C8. When we perform XOR on C7 and C8, what is C7? It is 0 and C8 is 0. Okay, and so the result would be 0. When the bits are same, it generates 0. So what will be our status flag? Let's say, yeah, what is V here? In this case, let me write it here. V is 0. There is no overflow. Okay, that is found by the result of this. The result is 0. Result of XOR is 0. Then V is set to 0. Means there is no overflow. Okay, and to set the other flags, how is it flag checked? the result is not checked, the result of this operation. Here the bits are all not zeros. Okay, if all the bits of this result is 0, then is it is set to 1. So otherwise it is set to 0. So this is the value of this Z flag is 0. And S, what is S here? Tell me what is S? What will be the value of sign flag? What would be the value of S here? What is S? S is F7, means the last bit of the result. The most significant bit of the result is F7. That is checked. So what is our result? What is the most significant bit of our result? Yeah, it's negative. Okay, so what would be the value of sign S flag? When the sign bit is 1, here this is our sign bit, right? Okay, this is F7. When these two are A and B, as per this, the result, this is F7. So F7 is checked. The bit is 1, so it indicates that the result is negative. Okay, so when the sign bit is 1, a sign flag, okay, this flag is set to 1, means it is negative. Okay, if the sign bit here is the most significant bit is 0, the sign flag is set to 0, indicates the number result is positive. Okay, so here after performing this operation, the value of S would be set to 1. And the other flag we have is carry flag. Okay, C. What is C here? Good, it is 0. Okay, why is it 0? Because there is no carry. Okay, the value of C would be 0 because C8 is checked. For carry, we check C8. Okay, C8 is 0. There is no carry, so this carry bit is set to 0. So this case, in our example, the status register, the 4-bit status register will have the value of V. First bit is V, correct? It is 0 and Z is 0 and sign is 1 and carry is 0. Okay, so from the status register, okay, it is understood that the operation performed, okay, there is an operation performed by the ALU and there is no carry out of the operation performed and the sign of the result is negative. Okay, the result is a negative number and this Z indicates that the result is all not zeros. Okay, that indicates it has some ones. Okay, so it is some other number, it's not all zeros, and there is no overflow. Okay, as B is 0, there is no overflow. Okay, this way the status register is used to set the status conditions. Okay, and why do we need this here? These status bits are used to check conditions. Okay, before branching, we can check the condition of these flag to understand the relationship between the numbers, input numbers A and B. And based on this operation, we want to perform some branching. Okay, we want to take the control of the execution of instructions to the different locations based on this operation. So such case, the status flag is checked. By checking this, based on that, we can control the execution of statements. Okay.